Hi everyone, and welcome to the new session of the Research Seminar series hosted by Nomadic Labs. Today's speaker is Aymeric Fromherz, a postdoc in the Prosecco team at Inria Paris. In this talk, Aymeric will give an overview of Fstar and its recent improvements. Fstar is a proof-oriented programming language with support for dependent types and user-defined effects. Fstar has been used to develop several real-world applications, including the EverCrypt cryptographic provider and the EverParse library of verified parsers and serializers. Feel free to ask your questions directly in the chat, and the Q&A session will happen at the end of the presentation.
Hi, and thanks for inviting me to speak today. It's my pleasure to be here to present some of the most recent work on Fstar, and in particular, the STEAL framework, developed with many collaborators listed here, which now enables the verification of concurrent programs in Fstar. To start this talk, I want to first give an overview of Fstar itself and of some accomplishments using this language in order to present the issues and challenges that led us to develop STEAL. As a language, Fstar combines several characteristics. First, it is a functional language, similar in syntax to languages like OCaml or F#, but it is also designed for verification of programs, making it proof-oriented. The core of the language relies on a rich type theory, with support for dependent types, similarly to proof assistants like Coq or Agda, but also for user-defined effects. And one of the specificities of Fstar compared to other type theory-based proof assistants is that it heavily relies on SMT solvers, in particular Z3, to discharge verification conditions, which significantly helps with automating verification. What this means is that occasionally, the programmer might need to add annotations and assertions or to call lemmas, but verification is semi-automated. And interestingly, Fstar also has support for metaprogramming and verification using tactics, similarly to Coq, for instance, which gives us more control when SMT-based verification is not sufficient. Now, before giving a concrete overview of Fstar, let me quickly describe what I mean by proof-oriented programming, which I use to describe Fstar as a language. Over the past decade, many successful projects showed that it was possible to provide formal guarantees about real-world systems, from compilers with ComCert and operating systems with SOL4 and Proven Core, to cryptographic libraries like Hacklestar and EverCrypt. And what all these projects have in common is that instead of trying to retrofit verification into existing code, for instance, written in C, these projects followed a proof-oriented approach, where proofs and programs were co-developed. And the idea is that a programmer often has a mental model of what the program should be doing, which guides the code they write. And in his book about the Iris language, Edwin Brady describes this methodology as a type-defined refined workflow. When the type system is expressive enough, as for instance in proof assistants like Coq or Fstar, programmers can write the specification of the model as a type before writing code. They then write the program that matches the type, and hence their model. And finally, they refine both the program and the type until both agree. And this is where verification happens. So following this approach greatly simplifies the verification effort, as the program is already structured with its specification and proof in mind. Now, on the other hand, co-developing proofs and programs can also simplify programming. And consider the simple example of a matrix addition. If we try to add two arbitrary matrices, we encounter a problem when the dimensions do not match. The implementation of the addition would thus need to handle these cases, likely raising errors. Instead, if we are working in a rich dependency type language, we can refine the signature of a function to statically ensure these cases do not happen. And here, you can see that we are parameterizing over two natural numbers x and y, and specifying that the two matrix arguments must have the same dimensions. And this allows for a very simple, intuitive implementation of matrix addition by statically preventing additions when matrix dimensions do not match. So this example is overly simplified for presentation purposes, but in my experience, co-developing proofs and complex programs is helpful to not just remove, but also identify unneeded cases and checks. Let me now present the Fstar language itself and some of its key features. At its core, Fstar is a functional language quite similar to OCaml. For instance, it supports recursive functions with a syntax that you might be familiar with. In this small code snippet here, factorial is a recursive function as described by the keyword rec, which takes as argument an integer n and returns an integer. And the body of the function itself is quite straightforward. If n is equal to 0, you return 1, else you compute the factorial as expected by multiplying n with the factorial of n minus 1 that you obtain by recursively decoding this function. And similarly to OCaml, Fstar also has support for inductive types and pattern matching. For instance, you can define the type of lists containing elements of type A as follows. You have two constructors, one for the empty case, which is therefore a list of A, and one for the non-empty case, which requires two arguments, HD and TL, in order to yield a list of A. And when manipulating an inductive type, you can then pattern match on its constructors. For instance, if you have a list L and want to implement a map function, you can apply a match on L to distinguish between the case where L is the empty list and where L is the concatenation of HD and the tail list. And see here how functions are first-class values similarly to OCaml. Map takes a function as argument, and we can pass it, for instance, this lambda, which increments an argument x by 3. Now, one important difference between languages like OCaml and Fstar is that Fstar's type system is more expressive, and in particular, it has support for refinement types. And to explain what refinement types consist of, I'll start with the standard example of natural integers. One way to see types in Fstar is as sets of values. What you sometimes want to do is consider restricted sets of values, or sets of values satisfying a given property. Natural numbers are such an example. You want to consider integers such that they are greater than 0, which is something we can specify in Fstar using this refinement here inside curly brackets. And we can use refinement types to define a variety of types. For instance, the type of strictly positive or negative integers, here called pos and neg, by again refining the type of integers int with a predicate. But we can also use them with other types. For instance, to consider only empty lists or only non-empty lists. Now, if you were to do pattern matching on a non-empty list, for instance, to retrieve its first element, one of the interesting things is that you do not need to consider the empty constructor anymore. Fstar can statically ensure that the empty case never happens, and it does so by relying on an SMT solver for all proof obligations related to refinements. So if you were to call non-empty HD with the list 1, 2, 3, the call would succeed and return 1. But if you were to call it with the empty list, the Fstar type checker itself would reject this program, and you wouldn't be able to compile it instead of raising an error at runtime in other languages. Now, in addition to refinement types, Fstar also has support for dependent types, that is, types that can be indexed by other types, but also by values. And for instance, we could define a type for vectors of type A and of length n. And here see that this definition returns an element of type, that is, it is a new type. And additionally, dependent types can be combined with refinement types, which can be very useful to specify pre- and post-conditions of functions. For instance, we could embed a specification for inc here inside its signature by stating that the return value, y, must be equal to x plus 1, where x was the value passed as an argument. And now, when defining the function inc, Fstar will only accept a definition that matches this step. For instance, if we were to define inc of x as x plus 2, the Fstar type checker would complain with the following error message, stating that it expected the return value here, x plus 2, to be an integer, while also being equal to x plus 1, which the SMT solver obviously cannot prove to be true. And if we instead define inc of x as x plus 1, Fstar now accepts this definition without any problem. One other key feature of Fstar that I've been omitting so far is its effect system. By default, all functions in Fstar are total. And for instance, here, this factorial function that I've shown previously actually has an effect, dot. And what this effect represents is that factorial is a function that always terminates and that has no side effect. That is, this is a pure function. Now, some of you might have observed that the signature of this factorial function is slightly different from the one I previously presented. Indeed, it takes a natural number instead of an arbitrary integer as argument and returns a NAT. And the reason for this is that without this change, Fstar's termination checker, which applies to all recursive thought functions, would fail. And indeed, if you can apply factorial to any integer, you can encounter problems. For instance, with this definition, factorial of -1 would loop forever, contradicting the meaning of this thought effect. And that's something the termination checker would catch, reporting that it could not prove that n-1 is smaller than n according to a well-founded order. And all of this is again discharged by SMT. Now, in addition to the thought effect, Fstar also provides primitive support for several other effects. And these include, for instance, the DV effect, which encapsulates possibly diverging, that is, non-terminating computations, but also the ghost effect, which represents computationally irrelevant computations that are commonly used for proof purposes. Think, for instance, of lemmas or assertions that will not appear in the executable code. And the important part about this is that, by default, functions with different effects are entirely separated from each other. For instance, if you have a function f, which has the DV effect, you cannot use this function inside of a thought computation. Trying to do so would yield a typing error, which would again be reported at compile time by Fstar. So what this means is that you cannot, for instance, use a divergent function for proof purposes or to write specifications. The logical total core of Fstar is completely separated from effectful computations, which is necessary for its soundness. But in some cases, it can be useful to, say, use total computations to define a divergent function. And to this end, Fstar allows you to define sub-effect relations. And defining this relation would allow the following toy program to be accepted by Fstar, for instance, which would allow us to use a total computation in a divergent context. Now, in addition to primitive effects like div, thought, or ghost, Fstar also allows a programmer to define their own effects using a monadic structure. And this is something that is invaluable when you want to define computations that operate on a state, for instance, or that can throw exceptions or even support I/O operations. Some existing programming languages allow you to do that using monads, and Fstar allows you to write and reason about such programs using monadic effects. And what this feature gives you is the ability to model different languages or programming idioms, such as side effects, in Fstar, as some kind of domain-specific language or DSL. And one such example is Lowstar, which I will quickly present next. Lowstar can be seen as the predecessor of Steel, which is the topic of today's talk. It is a shallow embedding, that is, it is a subset of the Fstar language, which models a small, well-behaved subset of C. And to explain how Lowstar works, I'll use this small memcopy function, which combines several of the Fstar features previously presented. This function takes as arguments two arrays, DST and SRC, which contain uint64 integers. And there is a condition on the source array, expressed here as a refinement inside the curly brackets, that ensures that both arrays have the same length. This function has the stack effect, which models C programs that only perform allocations on the stack. And this effect is user-defined. It is not primitive in Fstar, and it encapsulates that we are working on a model of C in Fstar. Now, as a precondition, this function requires both arrays to be live. That is, they are valid memory, they have been previously allocated and not yet deallocated, which will ensure memory safety. And the implementation is then very close to what you would expect in C. You read the first element of the source array and write it in the destination array, and so on. Ultimately, Lowstar code extracts to verified C using a compiler called Kremlin. And there exists a meta-theoretic paper proof ensuring the correctness of the extraction process. That is, that the extracted C code behaves as the Lowstar code that we reasoned about, and hence that all verification guarantees still hold on the executable code. Now, since Lowstar is just a subset of Fstar, verification conditions about Lowstar programs are discharged automatically using the Z3 SMT solver. And one of the interesting things here is that the restriction on the Fstar language in Lowstar only concerns actual code that will be extracted to C. To specify and prove a program, one can use the full Fstar language, for instance, through the use of a refinement for length. One of the biggest projects developed using Lowstar is Hacklestar and EverCrypt, a comprehensive industrial-grade cryptographic provider which is usable by unverified C clients and verified Fstar clients alike. Overall, EverCrypt is quite large for verification standards, totaling a bit more than 100,000 lines of verified C and assembly code at the moment. And since its release, parts of EverCrypt have been deployed in several high-impact projects, such as the Linux kernel and WireGuard VPN as part of a Zing crypto library, but also inside of Mozilla Firefox, the Tezos blockchains, and several others. But despite these achievements, using Lowstar was not always smooth, and the development of Hacklestar and EverCrypt required several person years. So what this means is that to scale to larger applications, it is necessary to bring the cost of verification down. And I will present next some of the challenges and limitations of Lowstar that we encountered while using it at scale, which led us to develop Steel. As mentioned previously, verification conditions in Lowstar are discharged through SMT solving. And while often convenient to reduce the proof burden on a developer, this also means that the SMT solver needs to reason about heap predicate, aliasing, framing, and so on, which becomes increasingly expensive as the size of programs and the number of arguments and memory objects grow. In cryptographic code, although sometimes tedious, memory reasoning is mostly straightforward, since data structures mostly consist of arrays of integers. But for more complex patterns, this quickly gets out of hand. And for instance, it took a PhD student close to 9 months to verify a low-level library for doubly linked lists in Lowstar. In addition to heap reasoning, the solver also needs to reason about many other logical theories at the same time. And this was especially problematic for cryptographic code because of its reliance on nonlinear modulo arithmetic, which led to proof instability. And we actually often had to disable nonlinear arithmetic reasoning in Z3 and instead do proofs somewhat manually by successively coding rewriting steps and small lemmas that could be proven in isolation when nonlinear arithmetic was not mixed with other theories. On top of all these specific issues, a full reliance on an SMT solver also limits the scalability of verification. And empirically, the verification time grows much faster than the size of the SMT context. And a too large context can send the solver entirely off the rails. And as such, we had to define precise curated abstractions to prune the size of the SMT context and break these abstractions in specific places to perform verification. For instance, the exact specification of a cryptographic hash is not useful to a client. It is sufficient for them to know it's a hash function. But the full specification is needed to prove that an implementation of a hash matches its specification. And finally, and most importantly for this talk, Lowstar only allows the verification of sequential code. And this was sufficient for cryptography. But unfortunately, systems programming often relies on concurrency. And for this specific issue, there is no possible tedious workaround. We need to improve the expressiveness of our verification frameworks to extend verification to a wider range of applications. And to do that, we need to look at different approaches to verification. One possible alternative to frameworks like Lowstar is to use separation logic, which I will quickly present. Separation logic is a Hoare-style program logic to reason about heap manipulating programs. And at the core of separation logic is the star operator, which specifies that two heap predicates, here P and Q, relate to disjoint separated parts of memory. Separation logic is designed to reason about framing in a modular way, using the frame rule here presented. And what this rule says is that if we have a program C such that, initially assuming Q, the predicate R holds after execution of C, here in the premise, then the execution of C leaves any separated predicate P unchanged. And to give a concrete example, let us consider the standard points to heap predicate, which states that the reference R is valid in the current heap, that is, it was allocated and not yet deallocated, and that it contains the value V. After writing the value 0 in this reference, the whole triple in the premise states that the reference is still valid memory and it contains the value 0. Now, using this frame rule, we can directly prove inside the logic that this write does not modify any disjoint part of memory. For instance, the value inside a disjoint reference S would be left unchanged. Over the past 20 years, separation logic has been an active research area, with many extensions to reason about concurrency, for instance, which is especially relevant to this talk, but also resource usage or probabilistic programs. And one of the biggest success stories recently is the Iris framework, which provides a highly expressive concurrent separation logic embedded in the cog proof assistant. And using Iris, different research groups provided many impressive proofs of intricate small pieces of code. But unfortunately, Iris is not a shallow embedding of concurrent separation logic inside of cog. What this means is that it does not allow you to verify cog programs. Instead, it applies to deeply embedded languages, for instance, the simple imperative heap lang, which is here used to implement swap. And somewhat surprisingly, no one has a practical concurrent separation logic with Iris-like expressiveness shallowly embedded within a dependency type language. The closest would be a framework called FCSL, which is a logic for verifying cog programs, but which does not handle, for instance, log allocation. And additionally, in Iris, verification is quite manual. It relies on interactively applying cog tactics, leading, for instance, to a proscript on the right to prove the correctness of this swap function. So, despite its high expressiveness, Iris has a fairly low level of automation. On the other end of the spectrum, we have frameworks like Viper, which offer auto-active verification, that is, mostly automated verification with occasional interactive verification. By limiting its expressiveness to first-order logic, Viper manages to heavily rely on automated SMT solving to discharge verification conditions, while allowing the user to interactively provide lemmas and assertions to help the solver. Now, even more on the left here, the Rust language has been gaining traction in the systems community. And Rust's ownership semantics can be seen as a lightweight version of separation logic, which can be entirely automated through type checking inside the compiler. In exchange, the expressiveness of Rust is more limited. For instance, Rust cannot model complex aliasing patterns such as doubly linked lists, and relies on an escape hatch called onSafe blocks to express features outside the scope of the language. So when looking at this graph, there seems to be a lot of unexplored space in the top right quadrant here. And creating a framework in this space is what we've been investigating over the past 2 years through the development of Steel. And before jumping into a detailed presentation of Steel and what we can already and hope to achieve with it, let me give a quick overview of what the framework consists of. Steel is a shallow embedding of concurrent separation logic in Fstar. And as such, it allows to specify and verify concurrent Fstar programs using the full power of a higher order dependency type language. Now, to prove programs, Steel provides an expressive, extensible program logic which contains many of the features of state-of-the-art program logics. And I don't expect you to be familiar with all of these things, but this includes the use of partial commutative monoids and dynamically allocated invariants, as well as an impredicative logic with support for monotonicity. But despite its expressiveness, Steel provides a fairly high level of automation through a cooperation between SMT solving and custom decision procedures for separation logic. And this is what already allowed us to write and verify a wide range of dependency typed libraries in Steel, ranging from standard AVL trees to concurrent queues, while also providing extensions of a framework for message passing concurrency using session types. And in the rest of this talk, I will now present Steel from the ground up, or rather straight from the anvil. And the core of the presentation will be about the examples we already wrote, but I will first give a quick high-level overview of the framework itself. The first step to verify concurrent Fstar programs is to define a semantic model for concurrency, which is captured by this function run that I will present quickly. We first define a model for concurrent Steel computations, which captures the structure of a program returning a value of type A under the precondition P and with a postcondition Q. Now, to define how Steel program executes, we provide an interpreter, the run function here, which takes a program as argument. And this interpreter has the effect NST. And what this effect captures is that the interpreter operates on a state, that computations are allowed to not terminate, and that programs are non-deterministic. And so the interpreter itself is defined as a non-deterministic interleaving of atomic actions. And finally, the interpreter is proven sound with respect to Fstar's type theory. That is, in its simplified version, assuming that the precondition P holds in the initial state M, the interpreter ensures that if the program terminates, the postcondition Q holds in the final state M1. And being able to prove this soundness property inside Fstar is one advantage of embedding still inside a proof assistant. We keep the same trust assumptions as Fstar itself. Now that we have semantics for concurrent Fstar programs, we need a logic to reason about them. And I will not go into too much detail about the still program logic today, but for this talk's purposes, it is sufficient to know that the program logic contains most of the features you would expect from a state-of-the-art concurrent separation logic. It has all the standard separation logic connectives, such as the star operator that I mentioned previously, but also the separation logic magic wand, as well as conjunction, disjunction, and quantification. And it also supports fancier features such as impredicativity and monotonicity. But the important part is that this program logic is entirely implemented and proven sound inside of Fstar with respect to our semantics. And as such, it is easily extensible with new libraries, as long as one can verify their soundness. So our semantic model and our program logic give us a basis to write and verify concurrent Fstar programs. Now, how do we verify them in practice? And in particular, how can we automate separation logic reasoning in STIL? One natural idea would be to encode separation logic reasoning inside existing SMT solvers. But unfortunately, despite their support for many logical theories, SMT solvers are not well equipped to handle separation logic. And there are several reasons to that. The first one is that separation logic is inherently higher order. Separation logic predicates are heap predicates, which are combined using different operators, such as the separation logic star. Second, many separation logic predicates are recursive. And this is the case, for instance, of predicates modeling data structures like lists or trees that need to be packed and unpacked during verification. And lastly, and perhaps more importantly, the separation logic star is associative and commutative. And as such, reasoning heavily relies on associative commutative or AC rewritings. For instance, to prove that P star Q star R is equivalent to R star P star Q, which is something that SMT solvers struggle with. So all of this seems to suggest that SMT solvers should not be used inside separation logic-based frameworks. But in our experience, SMT solvers are invaluable for scaling verification of concrete programs, in particular when reasoning about arithmetic or arrays and sequences. So how can we combine the two? There exists several solvers for separation logic, such as Smallfoot or Cyclist, but unfortunately, they commonly focus on restricted fragments of separation logic, and they do not support all the logical theories that SMTs can reason about, and that we need for verifying real-world software. So what this means is that we need a new approach which can differentiate between pure separation logic properties and SMT-based reasoning in order to use the best available tool for each verification condition. Now, to provide a high level of automation for STIL, one of our key ideas is to structure the STIL language to automatically separate between separation logic verification conditions and first-order logic verification conditions. And the idea we propose is to associate to each separation logic predicate what we call a self-framing selector. A selector can be seen as a view or evaluation of a given separation logic predicate in memory. For instance, the selector of a reference would be the value that it contains. We have a separation logic predicate pointer that encapsulates that we have a reference corresponding to valid memory. And its selector is the view of memory corresponding to its predicate, that is the actual value that it stores. And the self-framing property here ensures that selectors interact nicely with the separation logic frame rule that I presented earlier. Now, using selectors, programmers can then easily write specifications using first-order logic predicates that directly relate to selectors. And one simple example of this feature would be this swap function. Using selectors here, we can cleanly separate between separation logic reasoning about the shape of memory, here that we have two disjoint references P1 and P2, and between properties about memory contents, here that the value of P1 in the initial state S0 is equal to the value of P2 in the final state S1 and vice versa. So by separating both logics, we can therefore use the best tools available for each kind of reasoning. First-order selector predicates can rely on Fstar's native SMT encoding, to be automatically discharged by SNT solvers, while we developed a separate custom decision procedure that we implemented as an Fstar tactic to reason about separation logic calls. And importantly, all of this selector formalism is defined as an abstraction over the steel semantics and program logic, ensuring its soundness with respect to the steel semantics. And furthermore, by defining this decision procedure as an Fstar tactic, we also ensure its correctness with respect to Fstar's type theory. That is, we are not extending the trusted computing base of the Fstar framework. Okay, so after this quick high-level overview of steel, let me now show some recent examples that showcase the potential of the framework. And to start with, I will quickly present the implementation and specification of binary trees in steel, showing how we achieve the concise specs and high-level automation you would expect from heavily automated but less expressive frameworks like Daphne or Viper. We first define a standard type for tree nodes as a structure which contains some data and pointers to left and right subtrees. And a tree here is simply a pointer to a node. We then define a separation logic predicate, which captures that the tree pointer contains a tree-shaped data structure in memory. And using this predicate, we can then specify a standard hide function operating on binary trees. What this specification states is, first, that the function expects a tree-shaped structure and returns a tree-shaped structure after execution. It also ensures that the tree is left unchanged, and also that the return value, x, corresponds exactly to the height of a tree. Now, implementing the function matching this specification is straightforward and very close to what you would expect without verification. The only difference is the addition of the three statements here in green to reason about the recursive tree predicate. So verification here is mostly automated, and the only user interaction required is in specific deterministic places. And let me now show how we can extend this library to also provide self-balancing trees. When implementing AVL trees, most of the library is directly reusable. For instance, when specifying insertion in the self-balancing tree, we rely on the same abstract predicate for tree-shaped data structures as before. And the main difference is that we refine this predicate with an invariant, capturing the self-balancing nature of a tree, with the specification of this function stating that this invariant is maintained. And lastly, as for binary trees, we can express the functional correctness of this insertion function as a selector predicate, which gives us a clean and concise specification. And as for hide previously presented, the proof of insert AVL is almost entirely automated. The only user annotations required are calls to lemma for rolling and unrolling the recursive tree predicate in a few specific places. The next step in our steel tour is the implementation of concurrent libraries and data structures. And to enable concurrent implementations, I will first present an overview of our verified library for spin locks. A lock in steel is a value indexed by a separation logic predicate, which captures ownership of this predicate. And several operations are possible on locks. For instance, a lock can be acquired, transferring ownership of a predicate stored inside the lock to the program. And conversely, a client that acquired a lock and therefore has the predicate P in its context as a precondition can transfer ownership back to the lock by releasing it. And the postcondition, emp, here indicates that the client does not have ownership of P anymore after execution of a program. Steel also provides dynamically allocated invariants, which are very similar to lock. An invariant can be seen as a ghost lock, which will be erased at runtime, and it's also associated to a specific predicate P. And the idea behind invariants is that they can only be used inside atomic commands. That is, an atomic command is allowed to access the predicate locked by an invariant as long as it restores it after its execution. And an atomic command here corresponds to the composition of a physical atomic action, for instance, a compare and swap, and a finite number of ghost operations which can be used for proof purposes. Now, to separate atomic steel programs from generic ones, we leverage again Fstar's effect system and define a new effect called steel atomic. And for those of you familiar with the Iris framework, steel atomic also performs bookkeeping on an invariant mask to ensure that invariants cannot be recursively opened. And one of the interesting parts about using effects here is that we also define steel atomic as a sub-effect of steel. So this means that any steal atomic computation is automatically lifted to steal when needed by the Fstar type checker. And the converse is not true. That is, a steal computation can never be downlifted to steal atomic. This would yield a typing error. And this sub-effect relation is slightly simplified compared to what happens in practice, but the important part is that this lift preserves the separation logic specification P and Q. That is, steal atomic A, P, Q can only be lifted to steal A, P, Q, and not to different P prime or Q prime. And we also provide one last effect, steal ghost, which represents stateful ghost computations in steal that can be used for proof purposes, for instance, to call lemmas. And we also define it as a sub-effect of steal atomic, and therefore of steal, since this sub-effect relation is transitive, which enables us to easily use it in all steal programs. Now, invariants are freely shareable between threads, and as such, they enable log-free shared memory concurrency. Different threads can safely access the same part of memory concurrently, as long as it is done in an atomic manner. And using logs and invariants, I will now show how to model and implement concurrent queues in steal. One famous example of concurrent queues comes from Michael and Scott, and enables a DQ and an NQ operation to happen concurrently without any of the two locking the queue. And this structure is something we can model in steal, and although the exact details are out of scope of this talk, let me give you a quick idea of how this works. To enable log-free concurrency, we capture the shape of the queue as an invariant, which enables the DQer and the NQer to access it concurrently. To ensure that at most one NQ and one DQ occurs at the same time, we use locks to protect pointers to the head and tail of a queue. So a DQer, for instance, will have ownership of the head lock when performing the DQ operation. And one interesting thing about this structure is that it is not data race free. When the queue only contains one element, both the enqueuer and the dequeuer are accessing it concurrently. But nevertheless, we could both specify and verify the safety of an implementation of these two lock queues in steal, thus capturing an interesting concurrency pattern. Now, the last example I want to present today demonstrates how the expressiveness of steal allows to model more complex programming idioms, such as message passing concurrency as verified libraries. And our encoding of message passing concurrency in steal relies on something called session types. The idea behind session types is that we can associate a specific protocol to a given channel, and this is here captured by the separation logic predicate endpoint. And before I explain how we actually define this predicate using partial commutative monoids, let me present the interface of our library on a small example. Now, how would we use this to implement protocols? The first step would be to create a new channel for a given protocol P. And this is done here through this function new, which returns a new channel, as well as permissions for two parties to use the new channel for a protocol P. And the second party actually uses the channel for the dual protocol, where received and sent messages are swapped. Now, once we define protocols, we must specify when and how to send a message on a shared channel. And this is done through this function send. Initially, this function requires the permission to use channel C for protocol next. And the protocol must be in a state where we must send a message next, as represented by the predicate isSendNext here. And the message we want to send must also respect the specification of a protocol. That is, it must be compatible with the current state of a protocol. If all these conditions are satisfied, it is therefore possible to send message X on channel C. And after execution of the send function, we now have the permission to use the channel to execute the rest of the protocol. So all of these functions are entirely implemented inside steal as verified, dependently typed libraries. And the full library also contains functions with similar specifications to receive messages on a channel and also to close a channel once the protocol has been entirely executed. And as a concrete example, I will present the use of our message passing library in a simple ping-pong protocol. The specification of this protocol is quite simple. We send an integer, and we receive an integer that is strictly greater. And the interesting part is that we can use the full expressiveness of Fstar, including dependent types here, to state a relation between X and Y in order to specify this protocol. And this is one of the benefits of shallowly embedding steal into Fstar. Now, once specified, implementing this protocol is straightforward. We send an arbitrary integer, here picked to be 17, and we receive a second integer y before closing the channel. But the interesting part is this assertion, which ensures that the received value is greater than 17. And this assertion is entirely checked statically during verification. Since all messages exchanged on the channel must follow the protocol, y must always be greater than 17, the integer we send. And now, let me quickly give you the intuition behind our still encoding of this library. Our encoding relies on partial commutative monoids, or PCMs, which I will quickly present. Partial commutative monoids over elements of the type A have the standard monoid structure. There is a unit, 1, and a binary commutative operator, OP, such that the monoid laws are respected. The main difference compared to the standard algebraic definition is this composable predicate, which helps encoding partiality. And see here that the binary operator is only defined when its two arguments, x and y, are composable. PCMs have been used in a variety of contexts in separation logic to encode sharing disciplines, for instance. The idea is that if we have a reference R governed by a PCM P, and R points to OP of V1 and V2, then we can always split this into two disjoint separated points to predicates on V1 and V2 that represent partial permissions and can be given to different parties or threads. Now, our model of message passing concurrency rely on PCMs, but to start with, I'll use a simple example, a small stepper protocol. The idea behind this protocol is that we have two parties, A and B, which share an integer reference R. And we want each of these parties to take turns incrementing the reference. For instance, if R contains, say, an even value, A will first increment R by 1, followed by party B when R is odd, followed by A again, etc., etc. The question becomes, how do we give permission to both A and B to operate on R, while ensuring that they only do so in a way that satisfies the protocol? To do so, we will define a PCM operating on elements of type stepper. And this type will store the current permission that a party has on the reference, as well as the last value it wrote. For instance, a party can know that it must only operate on the reference when it is even or odd, and that the reference contained n last time this party wrote it. And we can also add the information that the reference is in a state where the even party is the next one that must increment the reference, and same for odd. And we also have two last elements to complete the PCM with a unit and an exclusive permission on the reference. Now, the interesting part becomes, how do we define the composability predicate and the operator to encode the stepper protocol? If two parties have knowledge even of n and odd of m at the same time, then the two sides must be at most 1 apart. That is, the absolute value of the difference must be 1. And additionally, if one party knows that it's the turn of the even party to increment the reference, then odd must be the last one to have incremented the reference, and it must be ahead of even. And I'm omitting the other cases here, which are similar for the sake of time. And now, using this predicate, defining the partial composition is straightforward. Gathering the knowledge of the two parties yields the real value in memory, which is the max of the last value seen or written by both parties. Okay, so we defined a PCM for this stepper protocol. Now, how do we actually use it in practice? And let me show this quickly when trying to increment the value from the even side. We will have a very similar function for the odd side that will operate concurrently. The first step is to read the current value of the reference x through the function readRefine. In addition to reading the value in memory, this function also refines our current knowledge of the state of the protocol in a way that is compatible with the PCM. So if the value in memory is different from n, that means it is greater than n and therefore odd. And it is our turn to increment the reference, which we do through right here. Else, the other party did not increment the reference yet, and we have to loop waiting for our turn. And so with that, we now have a model of how two parties can operate on a shared reference while following this stepper protocol. And in practice, we use a very similar approach to model generic protocols beyond just stepper. Our PCM for sessions is more complex and reasons on traces of exchange messages, but it has a similar structure and similar composable and composition operators. To wrap up this talk, I want to spend a few moments discussing what we achieved so far and presenting the next steps for Steel. With the development of Steel, we extend the Fstar to allow us to write and verify concurrent programs. And while we are still working on improving the programmability and usability of Steel, most of the pieces are already in place and we have several encouraging results. We already implemented a wide range of verified libraries, showcasing the expressiveness of a framework while benefiting from its high-level automation. And we also have several ongoing larger projects using Steel. For instance, we are currently looking at implementing and verifying a secure memory allocator, and also investigating how to use Steel to establish security properties about cryptographic protocols. And given our experiences so far, I believe that Steel has a lot of potential as a foundation for high-assurance systems programming. Thanks to its rich program logic, many programming idioms could be encoded as verified libraries, similarly to what we did for message passing concurrency. And possible future projects I'm interested in include the verification of low-level state machines, which we could integrate with verified parsers by building upon the EverParse project, an existing Fstar library of verified parsers and serializers. And another intriguing possibility would be the development of high-assurance Rust libraries by extracting Steel code directly to Rust. But the core idea is that by embedding Steel into an existing proof system, extending the expressiveness of a framework is always possible, and we've barely scratched the surface of the possible applications. If you're interested in using Steel or if you have potential applications ideas, please don't hesitate to drop me a line. All of our code is open source and publicly available on GitHub in the main Fstar repository. And with that, I want to thank you for your attention.
Okay, thank you for your presentation, Aymeric. Let's have a look at the questions in the chat. So we have a few questions on Fstar more generally. So Herman asks, what are the subtyping or subaffecting rules for Ghost? Can I use the type system to ensure that I'm not leaking auxiliary variables or Ghost state to extracted code when combining Ghost and other effects like ST? And he also asked that if the answer is yes, that would be a really cool feature, as it's painful to enforce this manually in something like a shallow embedding in Coq.
Yeah, so that's a good question. So the short story is the answer is yes, and that's indeed a very cool feature that we are very happy to have. To give a bit more details, the way it works is that you have a notion of erasable type in Fstar. For instance, unit is erasable, erased values are erasable, logical formulae are erasable. And the idea is that by default, you're going to have a lift that will be inserted from Ghost to, let's say, ST. But this lift will only type check if you are lifting an erasable value, meaning a value that will not be extracted at runtime. So for instance, if you have a Ghost function that returns an integer, and you try to lift this Ghost function to, let's say, ST, you would indeed have a problem that will be caused by the Fstar type checker, because you could have some notion of Ghost state leaking into the main computational context. In addition, you also have a notion of erasable effect if you want to define more complex Ghost effects. And for instance, in our code, the Steel Ghost effect is one example. So that's what allows us, for instance, to use Ghost function even with non-erasable type and directly lift them to Steel Ghost while having the Fstar type checker that will accept that, because Steel Ghost is erasable and will be extracted at computation time.
Okay. Another question, does Fstar have a core language based on a well-known formalism like CIC and Galena, asks Hans.
Yeah, so to the best of my knowledge, Fstar used to have a formalization using a Ghost language that was, among other things, modeling a primitive notion of the extra monad. There is a recent paper that is available on the Fstarlang webpage that tries to simplify these things by defining indexed effects, and the formalism there in the core language relies on just a core lambda calculus with dependent types and refinement types. That being said, I'm not completely sure how much it captures. Like, I'm not sure it captures all of the features of the actual Fstar language, and you do not really have in the implementation of a type checker a way to come back to this like low-level core language.
Mm-hmm. Could you elaborate on the partial evaluation or extraction features of Fstar? How do they influence the design of DSLs such as Steel? Another question from Hans.
Yeah, so I'm not exactly sure what you have in mind, but basically the idea is that extraction in Fstar, generally speaking, can be fine-tuned in the sense that you can instruct Fstar to normalize some terms before extraction, or to apply some rewriting rules, to perform some reduction. You can really fine-tune your extraction process. And in the past, that's something we've used heavily with Lowstar, for instance, in Hacklestar and EverCrypt, by having some code that was, for instance, taking functions as arguments, and then applying partial evaluation before extraction to get idiomatic C code in the end. So in a sense, I'm not completely sure if it impacts the design of new DSLs. It's more that it allows us to give full access to the Fstar language and all of its features, and just say, if at the end of the day, you indeed want to extract, let's say, Steal or Lowstar code to C, you need to apply enough partial evaluation, enough reduction, so that you get into the subset of idiomatic C code. So that's something that allows you, when you write Lowstar or Steal code, to have the full generality, parameterized by functions and so on, but still at the end have executable idiomatic code.
Right. So on that note, Shira also asks, so can we extract C code from Steal, or is that not something that's currently done? And
yeah, sorry.
No, sorry, go on.
Yeah, so we can already extract C code from Steal. The support is somewhat limited at the moment, but we have several libraries that are already extracting, and we are actively working on extending this and figuring out the last remaining issues. Yeah.
Mm-hmm. And in general, what are the limitations of Lowstar for verifying low-level implementations? Is expressiveness an issue? That was also a question by Shira.
I think it's more of a trade-off between what Lowstar gives you versus what Steal gives you, in the sense that early in the talk, I was presenting some of the challenges that we encountered with Lowstar. It was mostly about maybe overly relying on the SMT solver and not necessarily having a very structured way to reason about memory. And so that means, for instance, once you start having complex aliasing patterns, the example was doubly linked lists, that's something that is not so convenient to verify in Lowstar, and that can be actually quite painful, not to express it, because Lowstar has the expressness for this, but really just to do the practical verification and make sure that the SMT solver accepts the proofs that are given. So that's why, for something like doubly linked lists, for instance, separation logic is a better choice, but you also have patterns that are expressible in separation logic, but that are not necessarily a natural fit. Like, for instance, if you want to express that two arrays are disjoint or equal in separation logic, you can express this with a disjunction, but that's something that is a bit tedious to manipulate in your proofs. So, it's this kind of trade-off of you can express many things in both, but it's not necessarily practical to reason about them. So ideally, we would like to have the best of both worlds, of being able to interoperate between Lowstar and Steal to use each of them to the best of their ability.
Right. So Marco asks, is there any relation between Steal and DeviceStar? Perhaps you can see what DeviceStar is for the people who don't know.
Yeah, so DeviceStar is a new framework developed, among other things, at Inria in the Prosecco team, to reason about the security of cryptographic protocols in a symbolic model. So I'm not extremely familiar with DeviceStar. Like, I'm not one of the developers or implementers of DeviceStar, and I haven't personally used it. I'd say the relation is that both of them are frameworks implemented in Fstar, and DeviceStar, to the best of my knowledge, also makes use of the effect system from Fstar. But we do not have, at least not yet, any actual correspondence or interoperation between the two frameworks. That would be something interesting, being able to prove the security of some protocols in DeviceStar and then prove that an implementation in Steal matches the specification of a protocol that we have in DeviceStar. Yeah.
Is that something that's it's practical, like it's envisionable to combine these kind of frameworks that have been written in Fstar, or is it just a completely different work that it's not something entirely different that's not wouldn't build that much on the individual work on?
Yeah, I think it's something that we can imagine, at least. In the past, we've had experience combining several verification frameworks written in Fstar. For instance, we designed an interoperation between Lowstar and a framework called Veil that was doing verification of cryptographic assembly code. And so we designed a way to have the two, code in the two languages, in the two frameworks interoperating, to have unified verification guarantees and so on and so on. So It's a bit unclear at the moment how much work it will actually be for Steal and DeviceStar. But at the very least, you are in the same proof assistant, operating somewhat on the same logic. And it's more of a question of how can you unify the two abstractions in a sound and efficient way.
Mm-hmm. Marco also asks, other than concurrency, has the work on Steal improved the usability of existing Lowstar?
So the two of them are really separate in the sense of if you write Steal code, at least at the moment, you cannot reuse Lowstar libraries and you do not reuse like the Lowstar features themselves. So it's still, we are still working on the tooling, for instance, and especially on debugging features, error messages. Experiments so far are very promising in the sense, for instance, that implementing and specifying doubly linked lists in Steal, that's something that took us basically a few hours instead of a few months. But again, this kind of data structures is really, the core strength of separation logic. So is it a biased example? Maybe a bit, and that's why we're also interested in larger applications to really compare, let's say, the development of a big library with the development of EverCrypt in Lowstar.
Mm-hmm. Another question from Herman. The denotational semantics based on trees is very similar to FCSLs, but you get away with impredicative resources and avoid step indexing a la Iris. Is this related to monotonic state? What's the catch?
Yeah, that's a good question. So this is indeed related to monotonic state. The idea is that monotonic state is actually some kind of step indexing that is internalized in the sense that in Fstar, the model of monotonic state relies on witnessing stable predicates. But if you have witnessed, say, predicate P, you do not have P in your context. You have the predicate witnessed of P. And to actually retrieve P, you need a step of computation through a recall function, which would correspond in a sense in Iris to eliminating the later modality. So that's why, the idea is that we are literally internalizing this thing through ghost step of computations instead of having it explicit in the logic as Iris does. And if you want more detail, our Steal core paper from ICFP 2020 provides a full explanation, and I'd also be happy to chat about it offline.
So I wanted to ask you something about how verification works from the point of view of the user. So you mentioned that the key idea in Steal is that you separate predicates on things that you would prove in Fstar in general, and then predicates on separation logic. And then the first ones they get proved in a normal way in Fstar, which could be automatically directly by SMT or with lemmas, with tactics. But the separation logic predicates, are they always just proved automatically? Does the user have any kind of interactive control, or it's either it gets proved or not, and that's that?
Yeah, so the user does have a bit of control in the sense that our framing tactic, or we have a tactic or decision procedure that tries to do so automatically. But when it fails, and it does fail in some cases, it provides you, the context, the query that it tried to prove, and it explains, I had these things in my separation logic context that I tried to match with these things, and I couldn't match the two. I couldn't unify the two. And in this case, what the programmer can do is add manual rewriting steps. Say, for instance, actually, predicate P here in separation logic is equivalent to predicate Q. And here, they can use the SMT solver to help with the proof of this thing. They can use the SMT solver, or they can use lemmas, assertions, and so on. They have access to a full Fstar, and all of this goes to the SMT solver in the end.
And these rewriting steps are they something generic, or is these tactics specific for Steal?
It's basically a generic ghost computation in Steal, which literally says rewrites predicate P into predicate Q for separation logic. But it's just a Steal function, just a ghost Steal function.
Okay. I don't see any more questions, so I think we can wrap it up. Thanks again for sharing your knowledge with us. This was very interesting, and thanks everyone who attended this research seminar session. Have a nice day.